what impact will the warming of Antarctic deep water have on the North Atlantic sea level? Welcome, friends. Jim here. Warming of Antarctic deep sea waters contribute to sea level rise in the North Atlantic, a study finds. We'll go over this in a bit. Analysis of mooring observations and hydrographic data suggests the Atlantic Meridional Overturning Circulation, AMOC, deep water limb in the North Atlantic has weakened. 2 decades of continual observations provide a greater understanding of the Earth's climate regulating system. Okay, now, it's been documented and measured and so forth. Up here where the deep water formation occurs in the North Atlantic, yes, the deep water formation is slowing. You're not getting the sinking as much, basically due to the influx of fresh water. So you have freshwater land, decreases the salinity, decreasing the density, not as heavy, doesn't sink as much. And this has been documented since the late 1990s, early 00s. Norwegian researchers have noted this. Researchers from Dalhousie University in Nova Scotia, basically Dartmouth, Nova Scotia, Dartmouth, Halifax, kind of a twin city there. Nova Scotia is right about there. So they've been measuring this and quantifying the slowdown. A new study published in the journal Nature Geoscience, led by scientists at the University of Miami Rosenstiel School of Marine Atmospheric Earth Science and NOAA, found that human-induced environmental changes around Antarctica are contributing to sea level rise in the North Atlantic. Well, what's this all about? Research team analyzed 2 decades of deep-sea oceanographic data collected by observational mooring programs to show that a critical piece of Earth's global system of ocean currents in the North Atlantic has weakened by about 12% over the past 2 decades. Although these regions are tens of thousands of miles away from each other and abyssal areas are a few miles below the ocean surface, our results reinforce the notion that even the most remote areas of the world's oceans are not untouched by human activity, said the study's lead author, Tiago Bilou, an assistant scientist at Rosenstiel. The scientists analyzed data from several observational programs to study changes over time in a cold, dense, deep water mass located at depths greater than 4,000 meters. That's 2.5 miles below the ocean surface, or 4,000 meters, of course, is 4 kilometers, that flow from the Southern Ocean northward and eventually upwells to shallower depths in other parts of the global ocean, such as the North Atlantic. Okay, let me pull up this diagram here to kind of give you an orientation, is what they're talking about. So, here's Greenland, right? This is the Mediterranean intermediate water, right? Here's that branch going to Fram. So here's the deep water formation. Now, this is highly generalized, but it's to give you the idea. Here's the North Atlantic deep water flowing southward, upwelling in the Antarctic divergence area. Here's the Antarctic bottom water. Now, there's also deep water formation off Antarctica. Let's not forget that as well. Right? So, and we also have the Antarctic intermediate water, and here's that warm water that just kind of sits there between the 40s pretty much all the time. So what they're saying is that this is warming and pushing north. when AMOC weakens, this flow weakens, the layers, the intensity, the layers get thinner, the intensity slows down. The flow rate slows down. So to compensate, because we have a conservation of volume consideration, Antarctica bottom water picks up the slack, so to speak. And to some extent, the intermediate water as well. But you see the Antarctic bottom water infiltrating further and further north as AMOC weakens and slows. So this is kind of what they're getting at here. So when they say, located depths greater than 4,000 meters that flow from the Southern Ocean northward and eventually upwell to shallower depths in other parts of the global oceans, such as the North Atlantic. So this is moving this way and shallower going into the North Atlantic. That's the water mass they're examining. Okay, so the shrinking deep ocean branch, the scientists refer to, they call it the abyssal limb, part of AMOC, three-dimensional system of ocean currents, act as a conveyor belt, right? That's Wally Broker's term, to distribute heat, nutrients, CO2, other chemical species, right, across the world's oceans. The near bottom branch is comprised of Antarctic bottom water, which forms from the cooling of seawater in the Southern Ocean around Antarctica during winter months. Among the different formation mechanisms of this bottom water, perhaps the most important is the so-called brine rejection, a process that occurs when salty water freezes. Right? So you form the sea ice. Well, you got to get rid of the salt. That then makes what remains liquid more dense, and it sinks. Antarctic bottom water. Right? Just like up in the North Atlantic. Only the mechanism there is the Gulf Stream, or more accurately, the North Atlantic drift, which comes off the Gulf Stream. It's warm and salty. It gives off its heat to become cold and salty and sinks. So basically, it's already cold, but it's not very salty, so it freezes to become very salty and sinks. In the North Atlantic, it's warm, it gives off its heat to become cold and sinks, being already salty to begin with. As sea ice forms, it releases salt in the surrounding water, increasing its density. The dense water sinks to the ocean floor, creating a cold, dense water layer that spreads northward to fill all three ocean basins, Indian, Pacific, Atlantic. I've discussed that mechanism with you many times before. During the 21st century, the researchers observed that the flow of this Antarctic layer across 16 degrees north latitude in the Atlantic has slowed down, reducing the inflow of cold waters to higher latitudes and leading to warming of oceans in the deep ocean. Okay, let's dissect this. The flow of this Antarctic layer north of 16 degrees north latitude in the Atlantic had slowed down. So by slowing down, the inflow of cold waters to higher latitude reduced. And because it did, the deep ocean waters warmed up. Let's go back to that diagram. So 16 degrees north latitude, about here. Now, this is interesting because when AMOC slows down, because of volume consideration, this usually fills in the void, so to speak. Now they're saying this is slowing down, and apparently the waters here are warming up. This is a very interesting finding. So if it's warming up, there's going to be thermal expansion. thermal expansion is going to lead to sea level rise. So that could also therefore be that if AMOC itself in the North Atlantic is slowing down because it's not as dense and it's also warming up because of absorbing the energy from the atmosphere and the already existing ocean heat energy there, then this water here is overall probably going to be warmer. So this is a very interesting finding that they're reporting here. The areas affected by this warming spans thousands of miles in the north-south and east-west directions between 4,000 and 6,000 meters of depth. As a result, there is a significant increase in the abyssal ocean heat content, contributing to local sea level rise due to thermal expansion of the water. Our observational analysis matches with the numerical models, what the numerical models have predicted. Human activity could potentially impose circulation changes on the entire ocean. This analysis was only possible because of the decades of collective planning efforts by various oceanographic institutions cooperating and so forth. And the title is the study is titled "Weakening of the Atlantic Meridional Overturning Circulation Abyssal Limb in the North Atlantic." Now, before we get to this, one thing I wonder, takes a long time for the sinking to go from the surface down to abyssal layers. How much did they account for the lag? I'm sure they did. But the lag being how much of that heat, it takes time to get that heat from the surface to the abyssal depths there. So how much of this heat being measured is from 2 decades ago? Something that is a question that immediately pops into my head here. So let's take a look at this. All right, AMOC system ocean current circulates water within the Atlantic Ocean, bringing warm water north, cold water south. Right, the red path is salty warm waters. That's in the upper layers. Right, so this is supposed to represent the North Atlantic gyre. Okay, this is the North Atlantic drift. Right, this is where AMOC basically forms. Right? And the blue path is the colder, fresher waters. And it's also the deep layer. So I'm not so sure about the fresher, I'm not sure about the fresher there, because if it sinks, it's salty to begin with. I think that's an error in there in the diagram. And the purple path is extremely cold, dense bottom waters, the abyssal layer. That's off Antarctica, and we can see flowing north. This black box is kind of their little modeling area that presumably is around the 16-degree north latitude and a little bit north of vicinity. The study found the AMOC abyssal limb represented by the purple path. You can see the branch going to the Indian Ocean, indicated by this arrow here, has slowed down by 12% in the 21st century. This flow weakening is associated with the warming of the extremely cold bottom waters, leading to sea level rise in the North Atlantic. So they make this little model of vertical water distribution. And if you look here, the upper layer before 2000, the current upper layer, well, if the relative thickness is supposed to indicate anything, pretty much the same. Deep layer before 2000, current deep layer. Again, the thickness is about the same. The abyssal layer before 2000, the current abyssal layer. Well, now we see that it's a little thicker. And that's a little thicker. That's supposed to be presumably the warming that it's warmer, and therefore this indicates the thermal expansion, which increases the overall water column by about 2.8 millimeters, 3 millimeters taller. You're going to say 3 millimeters, big whoop. Well, what's the surface area of the Atlantic Ocean? That's going to impact, surface currents, coastal communities. Don't forget, you have Western intensification here. And another thing, I did a video on this some time ago, but ocean gyres are kind of being shifted northward. So if it's being shifted northward, how's that going to impact what goes on up there? So this is an interesting finding. It's almost counterintuitive for my way of thinking, because as I described earlier, when AMOC slows down, you don't have that deep water formation. You don't have that flow southward, as indicated by this blue arrow here, which means the Antarctic bottom water has to fill in the gap, so to speak. So if this is slowing down, as they're saying, and this is slowing down, what does that mean for that bottom water there? Is that going to become stagnant? Will that eventually lead to hypoxic anoxic situation? Will that not be ventilated? That to me seems to be the implications of that. That deep water area will not be ventilated, which means whatever nutrients, whatever dissolved gases are there, could potentially be sequestered on a very long time scale. We're talking millennia. These are the thoughts that are coming to my head as I go through their findings here. So just again, if this is slowing down, not reaching as far north as has been typical in the past, but is stopping here, and this is weakening, that means this region here, and by the way, right here's your 4 kilometers, 4 to 6. So we're talking right in here. This region could very well become non-ventilated. And that could eventually lead to hypoxic, maybe anoxic conditions. The implications of this are large, very large. So, very, very interesting findings. So until next time, thank you for your time.